Hello, everyone. So last time we looked at non-homogeneous systems, if you remember. Last time we considered x prime equals ax plus g of t, where g of t was a vector and a is a matrix here. X is also a vector containing our unknown functions, let's say x1 to xn. And we saw that the general solution can be written as x equals xc plus xp, where xc was the solution of x prime equals ax, the general solution of x prime equals ax. Xp was a particular solution for this system of ODEs. And how do we find a particular solution? So to find xp, we can use undetermined coefficients, which is the method we saw last time. Or we can use a variation of parameters. See below. So how do we use variation of parameters to find a particular solution? Let's remind ourselves about one dimension again. So in 1D, we wrote a particular solution, let's say yp as u1 y1 plus u2 y2 all the way to un yn. Where y1 to yn were the solutions for homogeneous equation. Where y1 to yn solutions of homogeneous equation. And we had formulas for u1 to un. So formulas for u1 to un derived before. In terms of integrals, if you remember, u1 was integral minus y2 times f divided by Wronskian, and similar formula for u2. Now, here, following this pattern, we want to write a particular solution for xp in a similar form. So now, let's generalize this idea. So we can write xp as, let's say, some v1 of t, x1 of t, plus v2 of t, x2 of t. So these are vectors this time. xp is a vector. x1 to xn are also vectors, which are the solutions for, or n linearly independent solutions for a homogeneous system. And then we multiply them with some scalars. So v1 of t and v2 of t to vn of t are scalars. Plus all the way to vn of t, xn of t. So if we compare this formula with this formula, You can see that these are similar. Here, y1 to yn are one-dimensional solution because we are in 1D. So there are solutions for homogeneous equation in one dimension. But here, xi's are the solution. These are vectors, n-dimensional vectors, because we are now in dimension n. So I can mention here that where x1 of t to xn of t, which are vectors, n-dimensional vectors, n-dimensional vectors are the solutions of the homogeneous system x prime equals ax. Are linearly independent solutions, basically, not any solutions, are the linearly independent solutions of the homogeneous system x prime equals ax. And v1 of t to vn of t here are scalars. They are not vectors, they're scalars, they're functions of t, but scalar, not a vector. So here, it's a scalar times a vector. This is a scalar. This is an n-dimensional vector. Scalar times n-dimensional vector will become n-dimensional vector. Similarly, this becomes n-dimensional vector. All the way to this becomes n-dimensional vector. You add them together, becomes an n-dimensional vector, which is what our particular solution. Now, this particular solution is a function of t because this is a function of t, the scalar here function of t, the vector here is also in general a function of t, all the way to this is a function of t, this is a function of t as well. So I can, if I want to specify, I have to say that, you know, xp of t, because this is also a function of t. So here, well, we already know x1 of t to xn of t. These are the linearly independent solutions of the homogeneous system. We already saw before how to calculate them or how to find them. Now, the question is, how do we find v1 of t to vn of t so that this becomes a particular solution for our system, for our non-homogeneous system, which is what we wrote here, x prime equals ax plus g of t. So the goal here is to determine v1 of t to vn of t so that xp of t above becomes a solution for this system x prime equals ax plus g of t. So first, we want to write this xp of t in the matrix form. First, let's write, let me call this equation, let me equation star maybe, or equation 1. First, let's write equation star above. In the matrix form. How can we write in the matrix form? So we need a fact from linear algebra. Recall from linear algebra. Suppose that A1 to AN are columns of a matrix A. Suppose that A1 to AN are columns of a matrix A, and usually if this is the case, the notation that we used would be A equals, let's say, A1 to AN. And suppose that V is equal to, let's say, V1 to Vn. Then A times V, so this is a matrix times vector. This has n columns, and this vector V has n rows. We know that if you want to multiply a matrix by a vector, the number of columns here should be same as number of rows here. And this is the case because this A has n columns, A1 to AN, which we can denote it this way, and V is a vector with n rows and elements, V1 to Vn. Then A times V can be expanded as follows. Expanded as follows. A times V equals A1 to AN times V1 to Vn. And we can write it as A1 V1 plus A2 V2 all the way to AN Vn. So this can be written A times V, this matrix times vector can be expanded this way. A1 V1 plus A2 V2 all the way to AN Vn. So please note here that each AI here is a vector. See, this A is a matrix. A1 to AN are columns of A, therefore each of them is a vector. But V1 to Vn, each Vi here is a scalar. It's a number. This whole thing, V1 to Vn is a vector, but each Vi is a scalar. So each AI is a vector, which is a column of A. Each Vi is a number. A1 times V1 becomes a vector. This is a vector, this is a number. A1 V1 becomes a vector, all the way to AN Vn becomes a vector. You add them all together, the result becomes a vector. So A times V is also a vector because matrix times vector is a vector. Matrix times vector is a vector. Left-hand side is vector, right-hand side is also a vector. So in linear algebra, you saw that A times V can be expanded this way. So if we apply this rule to the expression we had for xp of t, how can we write the right-hand side? So now if we apply, so let's apply this rule. Now let's apply this rule to equation star above. Then xp of t, which was a v1 of t, x1 of t, all the way to vn of t, xn of t, can be written as a matrix times a vector. Which matrix times which vector? So the matrix can be written as x1 to xn. Remember, xi's here are columns. These are vectors. So I can write this one as x1 of t to xn of t. And then v1 of t to vn of t. Which can be written as x, like capital X times capital V. Where capital X is defined as this matrix x1 of t to xn of t. And capital V is defined as this vector v1 of t to vn of t. Again, let me remind you one more time that each xi here is a vector, each vi is a scalar. So when I put these xi's together, this becomes a matrix because each of them is a vector. And when I put these vi's together, it becomes a vector because each vi is a scalar. And then capital X times capital V. So this will be capital X, this will be capital V. And capital X is the matrix whose columns are xi, and capital V is a vector whose elements are vi. Now this matrix X here is called the fundamental matrix of our system of ODE. So here this X called the fundamental matrix. So what is the fundamental matrix? The fundamental matrix is the matrix whose columns are the linearly independent solutions of the system, homogeneous system x prime equals ax. So each xi of t here is a vector, which is a solution for our homogeneous system x prime equals ax. And remember that we are assuming that x1 of t to xn of t are linearly independent. So this x, capital X, is a matrix, capital V here is a vector, and the particular solution, we wrote it as the fundamental matrix X, capital X, times this vector V. Okay, so now we need to have xp prime to be same as ax p plus g of t. Remember, xp is supposed to be a particular solution, so that means it should satisfy the equation, our ODE, which is x prime equals ax plus g. So xp should satisfy that equation. So xp prime should be same as ax p plus g of t. Now, what is xp prime here? So xp is a capital X times V, capital V. So what will be xp prime? Capital X prime. Remember, both x and v are functions of t. Look at here, both capital X and capital V are functions of t. So in order to calculate and in order to differentiate the right-hand side, I have to use the product rule. So capital X prime times V plus capital V prime times X. I cannot change the order because I'm multiplying a matrix with vector, so the order should remain the same. So capital X prime times V plus capital X times V prime. Now, what is capital X prime? So also note capital X prime will be x1, capital X prime. The columns of capital X are x1 of t to xn of t. So if I differentiate them, I get x1 of t prime to xn of t prime. And what is x1 of t prime? Remember, each xi is a solution for x prime equals ax. So x1 of t prime will be same as ax1. So xa of t solutions of x prime equals ax. So then this will be ax1 all the way to axn. ax1 of t all the way to axn of t. And I can write this one as a times x1 of t all the way to xn of t. This is also a fact from linear algebra. From linear algebra, we know that a times, let's say, b1 to bn. If b1 to bn are columns of a matrix B, then we can multiply A with B in this way. So A times B1 to Bn, we can write it as AB1 to ABN. And then we can write this one as, so we wrote it this way, like x prime equals ax1 to axn, which can be separated as A times B1 to Bn, because from linear algebra, we know that the matrix A times B1 to Bn, if B1 to Bn are columns of a matrix, can be written as AB1 to ABN. So here we had AX1 to AXN. We could write it as A times this matrix X1 to XN. And X1 to XN, we already defined it as capital X. So we can write it as A times capital X. So we showed that capital X prime is same as A times capital X. So using this, xp prime now, it can be written as, now capital X prime, we know is A times capital X. So A times capital X times V plus X times V prime. Capital X prime, capital X times V prime. This was capital V. And this is also capital V prime. So this is xp prime. Now, if I substitute back into this equation, we already simplified the left-hand side, the expression for xp prime. Now, this is supposed to be same as axp plus g of t. So substitute back. Back into xp prime equals axp plus g of t. Then we get A times capital X times V plus X times V prime equals A times XP. XP was capital X times capital V plus G of T. So now, see, the good news is AXV cancels out with AXV in the right-hand side. I can cancel this term with this term. So then I'll be left with X V prime equals G of T. Now, X here, what was capital X is the fundamental matrix. which is the matrix whose columns are linearly independent solutions of the homogeneous system. So again, we know from linear algebra that if we have a matrix whose columns are linearly independent, then it will be invertible. So let me mention this now. Capital X is the fundamental matrix whose columns are linearly independent and so capital X is invertible. So what can I conclude? I can conclude that capital V prime is equal to capital X inverse times G of T. Remember, our goal was to find V1 to Vn, which were the entries of this capital V. V1 to Vn, which are the entries of this capital V. And we already found that capital V prime is capital X inverse times G of T. So what will be V itself? If we found V prime, then V will be simply antiderivative of V prime. Therefore, capital V is equal to integral X inverse G of T dt. So XP will be equal to XV, which can be written as X times integral X inverse G of T dt. So this is a particular solution. This is called variation of parameters. Variation of parameters formula for finding a particular solution. Now let's look at an example. Example, find the general solution of this system. Let's say X prime equals -5, 1, 4, -2 times X plus e to power 2t times 6 and -1. So this is our matrix A, and this is our G of T, the vector. So what will be the solution? We know that the solution will be XC plus XP. So we know X is equal to XC plus XP. Now to find XC, we need to find the solution of X prime equals AX. The solution of X prime equals AX. So what should we do? First, we need the eigenvalues and eigenvectors. First, find the eigenvalues, eigenvectors. And so I need to solve for determinant A minus lambda I equals 0. That gives me determinant -5 minus lambda, 1, 4, -2 minus lambda equals 0. So if you solve this determinant equals 0, find the roots. You will see that there are two roots. Lambda 1 equals -1. So check that lambda 1 is equal to -1. Lambda 2 is equal to -6. And then you can find the eigenvectors corresponding to each of these eigenvalues. So again, check that. The eigenvectors will be C1 equals 1 and 4. C2 equals -1 and 1. So what will be the linearly independent solutions? We know that in the simple case of having two distinct eigenvalues with two eigenvectors C1 and C2, the two linearly independent solutions will be simply C1 e to power lambda 1t and C2 e to power lambda 2t. So here I can say that the linearly independent solutions of the homogeneous system x prime equals ax will be x1 of t equals c1 e to power lambda 1t, and that's going to be 1 and 4 e to power minus t, and x2 of t will be c2 e to power lambda 2t. So that's going to be -1 and 1, -1 and 1 e to power -60. So these are the two linearly independent solutions. And then xc of t will be a linear combination of these two. Xc of t will be some constant, let's say alpha 1 x1 of t plus alpha 2 x2 of t. And that's going to be alpha 1, 1 and 4 e to power minus t plus alpha 2 -1 and 1 e to power -6t. And what about the fundamental matrix? Once we have the linearly independent solutions of the homogeneous system, we can simply put them as columns of a matrix, and then the resulting matrix will be called fundamental matrix, which we denoted with capital X. So the fundamental matrix will be capital X equals x1 of t as the first column and x2 of t as the second column. And then that's going to be, so what is x1 of t here? X1 of t, if I multiply this e to power minus t into this vector, I'll get e to power minus t and 4 e to power minus t. And then the second column will be x2 of t, which is minus e to power minus 6t and e to power minus 60. So this will be our capital X. And then we need, if we want to find V, remember XP was capital X times V. And what is V? V is integral X inverse times G of t. We have G of t, we found capital X. Now we need to find X inverse, capital X inverse. So next, find capital X inverse. Next. find capital X inverse. And what do we get? So recall, how do we find the inverse of a 2x2 matrix? We know that if A is, let's say, A, B, C, D, then A inverse will be 1 over determinant, which is 1 over AD minus BC times D minus B minus C A. So here, capital X inverse will be, so we already know the values of A, B, C, and D. We just need to substitute into this formula. And then we get 1 over e to power minus 7t plus 4 e to power minus 7t. And then times e to power minus 60, e to power minus 60, and then minus 4 e to power minus t, e to power minus t, which is going to be 1 over 5 e to power minus 7t times, so 1 over 5 e to power, 1 over e to power minus 7t will be same as e to power 7t. So I can write this one as e to power 7t divided by 5 times the same matrix here, times e to power minus 6t, e to power minus 6t, minus 4 e to power minus t, e to power minus t. And then this will be e to power t divided by 5, e to power t divided by 5, and then minus 4 minus 4 e to power 6t divided by 5, e to power 6t divided by 5. So this is my X inverse. Now that we found X inverse, then in order to find V, we need to find integral of, here, integral of X inverse times G of T. So next find V, capital V, which is integral X inverse times G of T. So what will it be? V equals integral X inverse is what we had here, e to power t over 5, e to power t over 5, minus 4 e to power 6t over 5, and e to power 6t over 5 times this vector here, which is g of t. What was g of t in our case? Here, this is g of t, 6 e to power 2t and minus e to power 2t. 6 e to power 2t minus e to power 2t dt. And then this will be integral e to power 3t minus 5 e to power 8t dt. And then this is going to be integral e to power 3t dt and minus 5 integral e to power 8t dt, which is going to be 1 over 3 e to power 3t, and then minus 5 over 8, e to power 8t. And then, so this is my v, and then lastly xp. Xp was capital X times capital V. This is my capital V. I already found capital X and capital V. Capital X was e to power minus t minus e to power minus 60 for e to power minus 60, e to power minus 60, and capital V was this matrix here, 1 over 3, 1 over 3, e to power 3t, and minus 5 over 8, e to power 8t. And then we get 23 over 24, e to power 2t, and then 17 over 24, e to power 2t. So this is xp. And then lastly, the general solution can be written as xc plus xp. So x equals xc plus xp. xc we already found it, xp we already found it, we just need to add them together. xc was alpha 1 e to power minus t 1 and 4 plus alpha 2 e to power minus 6t minus 1 and 1. And then xp is this matrix, and I can take e to power 2t out. If I take e to power 2t out, and then the resulting vector will be 23 over 24, 17 over 24. So this is the final answer. This is the general solution of our non-homogeneous system. Okay, guys.